The Chapter 4 practice test, I think it has 46 problems. There's no way that I'm going to write a test with 46 problems. I would kind of think 30 might be the number of problems on the test. So some of these problems that I'm about to do aren't going to make it onto the test. But you need to know how to do them all, especially as you get higher in math. These are all kind of foundational problems, important techniques to be able to important kind of problems to be able to solve. So problem 1 and 2 just want me to add some polynomials. I drop the parentheses in number 1, and now I'm going to combine like terms. I'm taking the time to write the like terms next to each other, but you certainly don't need to do this. In fact, problem 1, I probably could go directly to the answer without showing any work, and that's completely safe to do. For me, I dropped the parentheses, didn't change any signs, and then I've grouped the x terms together and the constants together. To add the x terms, I'm adding the coefficients of 7 and 2. The constant, 5 minus 6, is negative 1. And when I go to write my answer, I have a couple ways to show that negative 1. I could show it as a plus a negative 1 or just a minus 1. These both would be acceptable answers. This is what I would generally write. Usually I don't write plus a negative. Problem 2 is the same style of problem. So I'm going to drop my parentheses. Since there's a plus between the parentheses, I don't need to change any of the signs. And now I'm going to combine like terms without showing the extra step. The first terms I'm going to combine are 7x squared plus negative 2x squared. Because the coefficients have opposite signs, I'm going to subtract the coefficients. And when you're adding or subtracting, the exponents don't change. So part of my answer is going to be a 5x squared. And then I'm going to do the 8x minus 6x by just subtracting 8 minus 6, getting a positive 2. And again, when I'm adding or subtracting, the variables have to be the same. They don't change when I add or subtract. Lastly, I'm going to work on the negative 4 plus 1. You're allowed to use your calculator on this test, so if you can't figure out what negative 4 plus 1 is, pull out your calculator and get a proper number. And I would probably write my answer like this, but you absolutely could write 5x squared plus 2x plus a negative 3, because plus a negative is the same as a minus of the positive. The next two problems are subtracting problems. If I had to guess from the last piece of paper, there'll be one of those, and on this sheet, there's going to be one of these, because they're asking the same skill. And if I'm trying to reduce the number of problems on the test, problems that are asking the same skill, I'm probably not going to take 2 when I can just take 1. In this problem, it's a subtraction problem. The first parentheses I was allowed to just drop. The second parentheses I had to change all the signs before I could properly drop the parentheses. I'm going to emphasize what I'm going to combine by putting the like terms next to each other, which are the 5x squared minus 7x squared, the minus 2x and minus 4x, the minus 5 and the positive 2. If I'm not good at working with signed numbers, 5 minus 7 is going to give me a minus 2 for the coefficient of the x squared term. Minus 2 minus 4, the coefficient of the x term is going to be minus 6. And minus 5 plus 2 would give me a constant of minus 3. Minus 5 plus 2 would give me a constant of minus 3, or negative 3. There are other ways to show this answer, but that's probably the way that I would generally show this. 4 is ugly because of the multivariables, but it's no different. I'm going to get rid of the parentheses. The first parentheses I could just drop. The second parentheses, I need to change the signs. The minus in front of that parentheses causes each sign to change. The negative 3x squared y, when I drop the parentheses, is going to turn to positive 3x squared y. The positive 4xy is going to turn to minus 4xy. The negative 3 is going to turn to positive 3. I'd probably from here write my answer, but I'm going to take the time to bunch the like terms together just so you can see what I'm actually combining may be easier than if I didn't take the time to rewrite this. But this line right here I probably wouldn't show. The line above it is probably safe to show because to think of the signs switched in my head, I'd probably mess up. So I'm combining like terms. After I clear the parentheses, like terms have the same variables and the variables have the same exponents. The first set of like terms, I'm going to add the coefficients and leave the variables and get 5x squared y. The second pair of like terms, I'm going to subtract the coefficient of 8 and 4 and get positive 4 and leave the xy. And then the constants, 3 plus 3, add up to be 6. The next two problems will probably again be condensed down to 1 on the test. They want me to find f plus g of 1, and f plus g of 1 is really the same as f of 1 plus g of 1. And what I'm going to do is in one parentheses, I'm going to figure out what f of 1 is, put a plus sign down, and in a second parentheses, figure out what g of 1 is. F of 1 is computed by changing each of the x's in the f function to 1. And that's what I did in my first parentheses. G of 1 you can find by changing each of the x's in the g function to 1. Technically, orders of operations would be doing exponents first, actually parentheses first, but inside the parentheses, the exponents need to be done first. I'm being probably more detailed than you need to. As I'm trying to get to my answer to number 5, I'm doing kind of one step at a time, and you might be able to bunch some steps together, and that would be good. So parentheses need to be brought down to a single number before I can get rid of the parentheses. And inside both parentheses, I need to do an exponent first. And then each parentheses has at least one multiplication. The second parentheses has 2 multiplications that I should do to get the parentheses simplified. In my efforts to get the parentheses simplified to a single number, so I did the 2 times 1 in the left parentheses, the 4 times 1 and 3 times 1 in the right parentheses. And now I'm about ready to not write my parentheses. My left parentheses simplifies to -2 because 2 plus 1 minus 5 is -2. And my right parentheses simplifies to +3. Once I get the parentheses down to a single number, I don't really need to write the parentheses anymore. And for a final answer, it's 1. It's just a coincidence that the 1 that my final answer is the same as the 1 that I plugged in. That's generally not going to happen. 6 wants me to find g minus f evaluated at -3, which is going to be found by finding g and taking g and evaluating at -3, evaluate f at -3 and subtract the results. Just like I did problem 5, I'm going to create a parentheses for evaluating the functions, and in this case I'm going to put a minus between because of the minus between the g and the f. I put the g first and the f second because that's how they're written. For g of -3, I'm going to change the 2 x's in the g function to -3. For f of -3, I'm going to change the 2 x's in the f function to -3. And now I'm going to be lazy, and you're permitted to be lazy on the test. Since this is just math I could do if I had to. Since we're in the calculator portion of our class, if you want to use your calculator to do some of the arithmetic, be my guest. So I just used my calculator to get that first parentheses simplified to the number 47. My calculator knows the proper orders of operations. Once I get that parentheses simplified to a single number, I don't need the parentheses anymore. I'm bringing down my minus sign. I'm going to use my calculator to figure out what the second parentheses simplifies to, and I get 10. So for a final answer, I'm going to get 37 because I'm just going to subtract the what each parenthesis simplifies to. And you can't see that so much. Next two problems are rules of exponents, just kind of one rule problems. In problem 7, I'm going to add the exponents. If you're multiplying and the bases are the same, you do the multiplication by not changing the base, but you add the exponents. You'll notice I snuck a 1 on this third x. If there's a variable written that doesn't have an exponent, there's an implied exponent of 1. For problem 8, if I'm dividing and the bases are the same, I'm going to subtract the exponents. When we get into the rule where you're subtracting exponents, you might get negative exponents. If you're clever, you probably could avoid the negative exponents, but this problem, I'll just subtract the exponents and get b to the 5th for my answer. For problem 9, when I have a parentheses that has straight multiplication inside and an exponent outside, I can clear the parentheses by attaching the exponent to any number or variable that doesn't have an exponent and multiplying the exponent by any number or variable that has an exponent. To finish this up, after I cleared the parentheses, making the problem 3 to the 4th, b to the 2 times 4 power, I'm going to figure out what 3 to the 4th is, which is 81, and I'm going to multiply the exponents, and for an answer to problem 9, it's going to be 81b to the 8th. I'm going to do the same strategy on number 10, but I have to be careful when I attach the exponent to the negative 2. So I'm going to attach the exponent of 3 to the negative 2. I'm going to multiply the exponent of 3 by of the x, that exponent of 3 by 3, and I'm going to attach the exponent to the y. I should be careful. Since the 2 is negative, when I attach the exponent to it, I need to keep it in a parentheses, just so I don't make a sign error. Now I'm going to figure out what the negative 2 cubed reduces to. That reduces to negative 8. I can do that in my head. I'm just showing you. You can use your calculator. I don't want you to make silly math errors. So use your calculator if you can't do the math quickly in your head, or quickly and accurately. And then I multiply the exponent on the x, and I left my answer just like that. For problem 11, I'm kind of thinking this as two separate problems. I'm thinking it as reducing the fraction 6 over 12, and I'm thinking of reducing the fraction y to the 12th over y to the 8th. If I think of it this way, I might write my answer differently than if I think of the problem differently. So I'm going to do this problem two ways to show you two different possible answers. Doing the problem this way, I'm going to reduce the fraction 6 over 12 to 1/2 by dividing the 6 by 2 and the 12 by 2. So the 6 over 12 reduces to 1/2. And for the y's, I'm going to subtract their exponents and get an exponent of 4. So one answer to this could be y 1/2 y to the 1/4. The other way to do this is to reduce that fraction 6 over 12 the same way, but instead of making the y a separate fraction, do the subtraction and leave the y in the numerator. If you're subtracting, the exponent in the numerator minus the exponent in the denominator, the variable winds up in the numerator. And this would give me an answer that looks like this, 1y to the 4th over 2, and I don't need the coefficient of 1 if I'm writing the y in the numerator of the fraction. These are equally correct answers. This top answer is probably something I'd write in a calculus class. This bottom answer I'd probably write in an algebra class. It turns out that some of the operations that we do in calculus, it's nice to have the fraction preceding the variable. 12's just multiplying the coefficients, adding the exponents on the variables. So to do 12, I'm going to multiply the 8 and the 5. I'm going to add the exponents of 2 and 4 on the x, and I'm going to add the exponents of 5 and 3 on the y. This is another problem where if you looked at my answer key, I probably wouldn't have anything written down but the answer. But the answer is 40x to the 6th y to the 8th. The more work you show, the more chances I have to give you partial credit, so it's good to show work. Similarly, 13, I would probably just write an answer down without showing any work. Really, 13, I need to think of this as having a times between the 5 and the x to the negative 4th. I'm going to turn the 5 into a fraction by writing it over 1. Any number, any integer could be made into a fraction by writing it over 1. And then I'm going to use my negative exponent rule to say that x to the negative 4th is 1 over x to the 4th power. Now I've got my exponents positive, and I'm multiplying fractions. To multiply fractions, you multiply across the numerator and across the denominator. When I multiply across the numerator, I get 5 times 1, which is just 5. And in the denominator, I get 1 times x to the 4th, and that's just x to the 4th. That's my answer. I can get from here to there without showing any work. Similarly, in 12, I can go from the problem to the answer without showing any work. This is the work that I would show if I was showing work, but you can do these in your head just fine. 12 has a fraction with a negative exponent, and negative exponents usually aren't our friends. And I like to make negative exponents positive as quickly as I can make those negative exponents positive. And if you have a fraction with a negative exponent, to make the negative exponent positive, you find the reciprocal of the fraction. Now I'm going to clear the parentheses. The inside of the parentheses has division and multiplication. It doesn't have any addition or subtraction. So I can clear the parentheses by attaching the exponent to any number or variable that doesn't have an exponent written, and multiply the exponent by any number or variable that has an exponent. So I attach the exponent to the 4, I attach it to the y, attach it to the 3 in the denominator, I multiply the exponent of the x. And now I could pull out my calculator if this wasn't so easy to do in my head to figure out how to simplify this. But I think that's adequate. So for an answer to 14, what I have on the screen feels good. 15, there's a couple different ways to do it. It's a matter of preference if you want to deal with negative exponents or not. In 15, I can think of this as 2 separate fractions, just like I did a few problems ago. This fraction, 24 over 12, is a beautiful fraction. It reduces to 2. So part of my answer is going to be 2. And for the z's, this is z cubed over z to the 7th. I don't know why I wrote 7 twice there. The one way to reduce the z's is just to subtract the exponents. Because anytime I have a fraction with like bases, you can subtract the exponents and fix the base to get to simplify that fraction or reduce that fraction. And I'm going to speed this up. I'm going to write this as 2 over z to the 4th because I've kind of sold myself short on room. And not even, let me write that as 2 over z to the 4th. That's probably the proper way to do the problem. There are definitely students that get really good working with negative exponents, and they find ways to avoid the negative exponents. And the way that I showed in the video, the alternate way to do this would be to not create 2 fractions and not introduce the negative exponent. I know that the z is supposed to wind up in the denominator when I look at the problem because the bigger exponent's in the denominator. So rather than doing what I did above, I could subtract the exponents, big exponent minus small exponent, and shove the z in the denominator because I know it's going to end up in the denominator. This is the avoiding negative exponent approach, and I don't know if that's too complicated, but a lot of students like this strategy. So I dealt with the variables. I did big exponent minus small exponent, avoided the negative exponent by realizing that if I did the subtraction big minus small and did it in the denominator, that my variable would wind up in the denominator. The fraction 24 over 12 still reduces to 2, and that 2 has to wind up in the numerator. My answers need to match, but my technique doesn't need to match up. This is another problem where I might just write the answer down without any work because it's the steps that are kind of minimal. So I'm going to do 16 two ways. The proper way to do 16 is to subtract the exponent for the x's to subtract the exponents for the y's. Because if you're dividing and the bases are the same, you subtract the exponents. And if there was an addition or subtraction between the x and the y, I couldn't do this. This is straight multiplication in the numerator, straight multiplication in the denominator. I'm permitted to subtract exponents for the variables. So I subtracted my exponents and I got x times y to the negative 1 power. The y to the negative 1 power I'll make as 1 over y to the first. The x to the first power I'll make as x. And I can think of this now as x over 1 times 1 over y. I don't need to write the exponent of 1. That's x times 1 over 1 times y. And that's x over y. That's a painfully slow way, but very accurate way. The way that uses the rules exactly how they're written. And if that's the way you want to do the problem, perfectly fine. And even if you're doing this way and you skip some of these steps, as long as you get down to this step, you're fine. The shortcut way to do this is if I'm dividing and I need to subtract exponents, the shortcut is to take the big exponent minus the small exponent and leave the variable where the bigger exponent is. So for the x's, I'm going to take 6 minus 5. 6 is the big exponent, 5 is the small exponent. Leave the x in the numerator because the bigger exponent's in the numerator. For the y's, I'm going to do big exponent minus small exponent. The big exponent is 3, the small exponent is 2. Leave the y in the denominator because the bigger of the exponents is in the denominator. This is going to give me x to the first in the numerator, y to the first in the denominator, and that's equivalently going to simplify to x over y. This is not really using the rules of exponents. This is using a shortcut. And again, if you're not happy with the shortcut, you can do all of this, some of this, as long as you can get to the answer x over y. The technique is kind of, flexible. 17 I could probably do on my calculator. This is negative 7 to the 0, or the opposite of 7 to the 0 power. This should be negative 1. If I wanted to think of this, I really do need to think of this problem as the opposite of 7 to the 0 power. And 7 to the 0 power is 1. This is going to be the opposite of 1. And the opposite of a number is the number with its sign change. The opposite of positive 1 is negative 1. This is probably the way you can think of it. Another way I might think of this is really negative 1 times 7 to the 0, thinking of that negative as being a coefficient of negative 1. And then the 7 to the 0 is 1. And this whole thing would reduce to negative 1. This is what I kind of did in the videos. This is maybe what I do in Math 120. And they're both good. For 18, when there's a negative in a parentheses, it doesn't matter. As a fact, if there's a 0 outside of parentheses, it doesn't matter what's inside the parentheses. A parentheses with a 0 exponent is always going to reduce to 1. It doesn't matter if there's a positive inside the parentheses nor a negative inside the parentheses. You'll see that that reduces to 1. A parentheses with a 0 exponent always reduces to 1. I couldn't do 19 or 20 on my calculator because of the variables. In 19, I have to think of the 4 and the x to the 0 as having a time sign between them. When there isn't a parentheses, the exponent of 0 in this case only applies to the x. X to the 0 power is equal to 1, but the 0 exponent doesn't impact the 4. So the answer to 19 is going to be 4. 20, if you have a parentheses with a 0 exponent, it doesn't matter what's inside the parentheses, that's going to reduce to 1. So the answer to 20 is just going to be 1. 21 I'm going to distribute to clear the parentheses. I'm going to multiply 3 times 5x, or 3x times 5x. I'm going to keep the plus sign between, and I'm going to multiply 3x times 2. For the 3x times 5x, I multiply the coefficients of 3 and 5. I add the implied exponents of 1 and 1 on the x's, and my first term is going to be a 15x squared. I'm going to bring my plus sign down. For the second multiplication, I'm going to multiply the 3 and the 2, and I'm going to leave the x. For an answer to 21, it's 15x squared plus 6x. You shouldn't get a 21 in your answer because these aren't like terms. You can only add or subtract if the variables are the same and the variables have the same exponents. 22 is a foiling problem, so I'm going to do the foiling. The firsts are 3x times 4x. The outers are 3x times 5. The inners are minus 7 times 4x. The lasts are minus 7 times 5. So my first, I multiply the 3 and the 4 and get 12. I multiply the x and the x by adding the implied exponents of 1s and get an x squared. The outers, I multiply the 3 and 5 and get a positive 15. I write the plus sign down, followed by the 15. I need the x, but the x doesn't change for that multiplication. For the inners, I multiply the negative 7 and positive 4 and get negative 28. I keep the x. For the last, negative 7 times positive 5 is negative 35. Usually when you FOIL, the outers and the inners can be combined, and that's the case here. I need to take 15 and subtract 28 to figure out the coefficient of the x term, which is going to be minus 13. My answer for this should be 12x squared minus 13x minus 35. Can't simplify that anymore because there aren't any more like terms. In problem 23, I need to rewrite it so I can turn it into a foiling problem. The plus between the 3x and the 4 makes it illegal just to square the 3, square the x, square the 4. If this was 3x times 4, if the problem was 3x times 4 squared, then you could square the 3, square the x, and square the 4. That would be legal. But the plus sign between the 3x and the 4, that plus sign makes the process of just attaching the exponents illegal. So this right here would be done if the problem had a times between the 3x and the 4. Because it has a plus between the 3x and the 4, I need to rewrite it without the square with repeat multiplication and then do the foiling that's implied by this repeat multiplication. This is another problem I could do in my head, and you might have been taught in high school how to do this kind of multiplication in your head, and that's fine. So if I could do it in my head, I believe you could do it in your head. But if you start doing problems in your head and you make mistakes, then your partial credit goes to 0 and you start losing points that you wouldn't have lost if you showed work and I could figure out what your mistake is. But there's an answer for 23. 24 just asks me in function notation to multiply the f function times the g function. Super easy to do that. I'm going to create 2 parentheses with no sign between to indicate the multiplication. Inside the first parentheses, I'm going to put the f function. And in the second parentheses, I'm going to put the g function. And now I'm just going to FOIL. First are going to be x times 2x. Outers are going to be x times 1. Inners are going to be 6 times 2x. Lasts are going to be 6 times 1. For the first multiplication, I'm going to leave the 2 as a coefficient. I'm going to add the implied exponents on the x's, and my first term is going to be 2x squared. Second multiplication gives me a positive 1x. I need the plus sign between. Third multiplication gives me a positive 12x. I need the plus sign between. Fourth multiplication gives me a positive 6. I need the plus sign between. Normally when I'm foiling, the outers and the inners can be combined because they're like terms, and that's exactly the case here. And that would be a perfect answer for 24. Part B of number 24 wants me to multiply f evaluated at 2 times g evaluated with 3. Just like I started off with 24a, I created two parentheses with the implied times between. They're touching. That implies a time. In the first parentheses, I'm using the f function. I'm changing the x to 2. I'm not using a parentheses because it's a naked x. The x doesn't have a coefficient nor an exponent. In the second parentheses, I'm changing the x to 3 because in the g function, I'm supposed to put in 3. Now, each parentheses, I'm going to get down to a single number. The first parentheses is just easily 8. It's just 2 plus 6. And the second parentheses, I can do that in my head. That's 2 times 3, which is 6. 6 plus 1, which is 7. And then I'm going to multiply the 8 and the 7, and I'm going to get 56 for an answer. Do a few more, but eventually we'll get to a part 2. 25, it's a fourth root, and there's a multiplication. I need to separately take the fourth root of each of the pieces. On my calculator, if I do shift and the square key, I can do the fourth root of 16. If it doesn't come out to a decimal, I could use my calculator answer. If it comes out to a decimal, I need to simplify manually. But it comes out perfectly. So part of my answer is going to be 2. And for the z, if I could take the exponent of the z and divide it by the index, if you don't get a fraction, that's the simple way to reduce the radical. And these problems are from the beginning when we started reducing radicals. They work in the simple way. So 2z is the answer to 25. For 26, I need to find the square root of each coefficient and the square root of each variable. I know the square root of 9 is 3, and I know the square root of 49 is 7. I could use my calculator for it. And I can tell ahead of time that I could reduce the variables by dividing the exponent divided by the index. In a square root, there's an implied 2, that's the index, and you're always allowed to reduce variables by dividing the exponent by the index, but the only time it's really acceptable for an answer is if you don't get a fraction when you do that division. If the division results in a fraction for the variable's exponent, then you have to do the grouping simplification. So for my answer, I get 3x in the numerator, or 3x to the first power, and y squared in the denominator. Let's pause and do a part 2.